Welcome to the Introduction to Process Simulation with Aspen HYSYS, led by Associate Professor Dr. Mohammed Kamaruddin Abdul Hamid from the UMS Chemical Engineering Program. This course provides essential foundations in modern process modeling. Through step-by-step guidance, you will learn how to build, analyze, and evaluate realistic chemical process flows. Start developing the competencies needed for today's engineering challenges. Discover how Aspen HYSYS unlocks real process understanding through powerful simulation. Built on strong thermodynamics and trusted across industry, it helps you model steady-state and dynamic systems with confidence. This beginner-friendly guide walks you through core fundamentals, making process simulation clear, practical, and ready for real engineering challenges. Getting started in Aspen HYSYS begins with setting up your simulation basis. Create a new case, add your chemical components, and choose the right fluid package. Then move into the simulation environment, build your flow sheet, and specify your material streams. Watch the stream colors to check if your inputs are complete and your model is fully solved. Begin your Aspen HYSYS workflow by defining the simulation basis, choosing your components and equation of state. Next, set the stream conditions for temperature, pressure, and flow rate. View the calculated results in the workbook. Then analyze and compare using case studies or different EOS models to understand how the process behaves. A pump pushes scalding water from 3 bar to 84 bar, but with only 10% efficiency, something dangerous happens. As the simulation unfolds, the flowsheet exposes the hidden truth. Wasted mechanical energy turns directly into heat. The outlet temperature surges by 18 degrees, revealing how an inefficient pump can quietly overheat your entire process. A natural gas stream enters at mild conditions, but a compressor running at only 30% efficiency is about to change everything. As pressure rises from 1 bar to 5 bar, the simulation exposes the hidden heat trapped inside. The outlet temperature surges by an astonishing 248 degrees, revealing the intense thermal impact of compression and inefficiency. A high-pressure gas enters at 20 bar. But when it races through an expander running at only 30% efficiency, everything changes. The simulation reveals a dramatic chill. The temperature plunges from 25 degrees to below freezing at -6. The message is clear. Lower efficiency means weaker cooling, and the expander cannot deliver its full power. In this simulation, hot water transfers heat to a colder stream, and our goal is to find the cold stream's required flow rate. After defining the basis, adding both streams, and inserting the heat exchanger, Aspen HYSYS performs the calculations. The result reveals the answer. The cold stream must flow at about 55 kilograms per hour to reach the target outlet temperature. In this simulation, methane and air come together at the start of a powerful reaction story. We define the chemistry, build the flow sheet, and create the conversion steps that drive the transformation. As the reactor is placed and the reactions are linked, Aspen HYSYS brings the process to life, revealing how simple feeds ignite into a fully simulated chemical conversion. In this simulation, we bring the water-gas shift reaction to life. We define the chemistry, build the equilibrium reaction, and set the stoichiometry that balances carbon monoxide, steam, and hydrogen. As the reactor is placed and the reaction set is linked, Aspen HYSYS unleashes the solver, revealing the transformed outlet stream and the rise of hydrogen at equilibrium. In this simulation, propylene oxide and water enter a journey of controlled reaction. We define the chemistry, set the kinetics, and build the flow sheet that feeds a continuously stirred reactor. As the CSTR mixes and transforms the components, Aspen HYSYS reveals the outcome. At 75 degrees, the system achieves over 40% conversion, bringing the reaction to life on screen. In this model, 3 feed streams of air, steam, and water enter the flash separator. After defining the simulation basis, we add the separator and let Aspen HYSYS bring the mixture to equilibrium. The vessel then splits into vapor and liquid phases, and the workbook reveals the final outlet flow rates for each stream. From a single stream of natural gas begins a high-stakes separation journey. The demethanizer strips out methane with razor-sharp purity. The deethanizer pushes deeper, controlling the C2 to C3 split with precision. Then the depropanizer delivers the final cut, isolating propane and locking in product purity. Step by step, the NGL plant transforms raw gas into valuable liquid power. Every great engineer begins with curiosity, and you've just taken an important step forward. Through Aspen HYSYS, you explored how simulations turn complex processes into clear, confident decisions. Keep pushing boundaries, keep learning, and let every model you build strengthen your impact as a future-ready engineer. Your journey does not end here. This is only the beginning of what you can achieve.